Chemical equilibrium is when the concentrations of all reactants and products remain constant with time. Notice it doesn't say equal, constant with time. This is a dynamic equilibrium, meaning a state of balance between continuous processes. So the reactants will continue being products and products will continue becoming reactants. We can see this in graph form. The green line represents our reactants. Notice that they're decreasing over time. My products are increasing over time. I reach equilibrium when they are no longer changing. So from the purple line over, we're at equilibrium. We can see the rate of the reactions. The forward reaction is decreasing much faster because I have a higher concentration of reactants. And then my reverse reaction is slowly increasing. And I'm at equilibrium when my forward reaction equals the reverse reaction. That's that dynamic equilibrium. The forward and reverse reactions are still taking place. They're just taking place in a rate that's equal to each other. When you're given an equation and you have to calculate the equilibrium expression, also referred to as the law of mass action, you're going to do products over reactants. And this is a capital K. So we have our products raised to the power of the coefficient. So C to the power of M, D to the power of N, and then my reactants are on bottom. A to the power of J and B to the power of K. One word of caution, you're going to omit all pure solids and liquids. Solids and liquids are never going to go in your equilibrium expression because you cannot change the concentration of a pure substance. It's always 100%. So only aqueous and gases go in an equilibrium expression. So here we're going to write some equilibrium expressions. The very first thing you want to do is cross out all solids and liquids. In the first example, we don't have any solids or liquids. So we're going to just say K equals, and then my products, NO2, brackets mean concentration. So the concentration of NO2 to the fourth power, getting that from the coefficient, times the concentration of water to the sixth power over my reactants, so NH3 to the fourth power, and finally oxygen to the seventh power. So that would be your equilibrium expression or your law of mass action. Let's do one more together. For the second one, remember step one is to cross out all solids and liquids. Well, that's a solid, that's a liquid. So K is equal to chlorine. And that's to the first power, so it's just K is equal to my chlorine concentration. Also, always double check that your equation is balanced. All right, go ahead and pause the video and solve these last two on your own. Restart when you have your answers. Those two should have been crossed out, giving you water to the concentration or to the power of the fifth. And the second one, you should have crossed out that solid and that liquid. In this case, I don't have a product, so it's 1 over chlorine to the sixth. These problems say calculate the equilibrium constant for the following reaction, and they give you equilibrium concentrations for everything. So step one is write your equilibrium expression. Restart when you have your equilibrium expression. So you should have gotten that. The only one that was to square is our product. Now you're going to plug everything into your equilibrium expression and then solve. Restart when you have an answer. When you plug it in, make sure you bring over that square. A common mistake is writing the square over here and then forgetting to carry it over. So this should be your work. If you plug it in correctly, you should get 14.46. All of our numbers are in 3 sig figs, so we can say 14.5. There are no units on K, so just 14.5. Go ahead and pause the video and calculate K for this one. Remember, make sure that you're writing your equilibrium expression before plugging into K. So your equilibrium expression should have been that, and your answer should have been A. If you got A, you can fast forward. Otherwise, you should have put 0.02 on top times 0.02 over 0.21. Make sure you're multiplying and then dividing. So on this problem, they want you to calculate the equilibrium constant for experiment 1 and experiment 2. So step 1 is you need your equilibrium expression. So go ahead and pause the video and write your equilibrium expression. That's what you should have gotten for your equilibrium expression. Now you've got to look at experiment 1. And of experiment 1, if we're trying to find the equilibrium value, do we want the initial or the equilibrium values? If you said equilibrium, you're correct. We do not care about the initial in this problem. We're going to just plug in the values at equilibrium since we're just trying to find K. So we're going to plug in your values for equilibrium constant for experiment 1 and then for experiment 2. Restart when you have your K values. So for experiment 1, you should have gotten 4.35. And for experiment 2, you should have gotten 4.32. So what do you notice about the K values in experiment 1 and 2? They're not exactly the same, but they're really close to being the same. Because this is experimental data, the numbers are slightly off, but they're the same because equilibrium constants do not change unless we change the temperature. So it doesn't matter that we started with completely different numbers. When we reached equilibrium, our equilibrium constants were the same. So again, the values are the same, minus a little difference due to experimental error. So they're the same because equilibrium constants do not change except with temperature. Make sure that you've written that in the box on the right. So we can also manipulate K. If a reaction is reversed, then K will equal 1 over K because we're flipping the reactants and products. If an original reaction is multiplied by some factor, we'll say that factor is n, then K will equal K to that nth power. If given two equations and K's that add up to a new equation, we're going to multiply the K's to get the new K for that new equation. So let's see that in action. So on this one, we have a balanced equation. So we just need to write our equilibrium expression and then solve for K. Restart when you have the value for K. So in 2 sig figs, you should have gotten 38. So looking at this equation and looking at this next one, they reversed the equation. So remember that if it's reversed, we're going to do 1 over K. Well, our K was 38, so 1 over 38 is equal to 0.026. So if we look at our first equation, we look at this one, we've divided everything by 2. So 1/2 the original. So that's K to the 0.5. We've multiplied everything by 1/2. So that's 38 to the 0.5, which gives us 6.2. Go ahead and plug into your equilibrium expression and solve for the value of S8 algebraically. Restart when you have an answer. If you said C, you are correct. If you didn't say C, then let's see where you messed up. In this problem, they gave you the K value. So we multiply by 1 times, or 1 to the 8th, which is still 1. Then divide by 7.8 times 10 to the 4th to the 8th power. And then you should get the value that was up there a second ago. So 9.5 times 10 to the negative 5th. Since we're solving for concentration, it should have unit of molarity. This one wants the reverse reaction. So I'm going to restart when you have your answer. You should have gotten B because it's just 1 over K, or 1 over our 9.5 times 10 to the negative 5th. When you're trying to solve equilibrium and it's only dealing with pressure, sometimes they'll say, what is the KP? KP is equilibrium constant involving pressure. It's going to be solved the same way as K, but you will use the pressures at equilibrium instead of concentrations. So we can't use brackets because brackets mean concentration. We're going to have to use parentheses. So for my KP, it's going to be pressure of SO3 to the 2nd power over pressure of SO2 times the pressure of oxygen. So that's my KP expression. Notice no brackets, and it's pressure of each one. Go ahead and write your KP expression and then plug in your values to solve for your KP for this one. Restart when you have your answer. So that's your KP expression. Plugging everything in, you should have gotten 1920.